In this lesson, we're going to look closer at the integral relationship between velocity and what it can do to help us find positions, displacement, distance traveled, all that kind of stuff. And I know this is a little bit blurry, so after this just kind of preliminary scenario, I'm going to ask you to get this handout ready to go so that you can follow along as we go through that. So we're going to let x of t be a function that represents the position of a particle. We're going to call him particle boy at time t, and we're going to measure time in seconds. Now, this is his initial position, so you can designate that as x at time 0. And you can see from the diagram that x at time 0 is 2 on the number line. So let's say 10 seconds later, we find particle boy sitting right here, or standing right here, at position x equals -3. That means x at time 10 is -3, and that's his end position. So he started at position 2, and he ended up 10 seconds later at position -3. So we know that his displacement is found by doing the calculation of the difference between these two. So displacement is his position at the end, x at time 10, minus the position he started at time 0. So in this case, it's -3 minus 2, or -5. And what that means is essentially he is now 5 units behind. Since it's negative, he's 5 units behind where he started. And that's pretty clear in the picture. He just came from here, and it's 5 units back. Now, it might surprise you to realize that that doesn't mean he traveled 5 units back. He did not necessarily take 5 steps backward. What else might have happened? Well, he might have actually started moving forward. So when he started, he was headed this direction. Maybe he goes 3 units this way, +3. Then he turns around and backs up, comes back to position 0. So he goes back 5 units. Then he decides to make another turn, goes forward 2 units, stops and says, hey, I've been here before, but then he decides to go forward again, and he goes forward, we'll say 4 units. At which time he decides to turn back around and just keep on walking, and there he ends up at his same end position. So that last move was back 9 units. So if that's the actual scenario that happened, we have more than just a start and an end position. We actually know the path he took. His displacement hasn't changed. It's still -5. But now we can ask the question, how far did he go? In other words, what was his total distance traveled? So total distance is done a little bit differently. He went forward 3, then he went 5 units back, but we don't really care that it was going back. The distance he covered was 5 units. So maybe I'll make that +5 there. And then he went forward 2, then he went again 4 forward, and then he went back again, but I don't care that he was going backwards. I only care about how far he got. So then he moved 9 units. So his total distance traveled is, oh, here we go, 8, I think that comes out to be 13 units of distance traveled. Displacement, back up here, could also be calculated with these same values, but we do have to pay attention to the direction that he went. So another way to calculate displacement would be to, following his path, count everything in the positive or in the negative direction as it applies. So +3 for his forward move, back 5, let's subtract, +2, +4, then back 9. When we calculate all of this, I believe it comes out to be -9, or I'm sorry, -5, and sure enough, and it should, because that's his displacement. So displacement takes into account the direction, but total distance traveled means we don't care about direction, we just want to get an accounting of how far he went. All right, so that brings us to our note sheet on net change. And this kind of just rehashes that same discussion. If you are taking 2 steps forward and 1 step back, if you want to know how far you traveled, that's total distance. Well, you traveled 3 steps total. 2 steps in the forward direction, 1 step in the backwards direction. We don't care which way you were going. It was a total of 3 steps. But displacement is about where you are compared to where you started. So it's the difference between those two. If you went forward 2 and back 1, your displacement is the difference between those two, the start and the end value. So it's this distance right here, which would be 1 step. And not just 1 step, but since we care about direction, 1 step forward is the displacement. So keep those 2 things in mind as definitions as we work further with velocity and its relationship to these ideas. All right, here's some important formulas or definitions to know. If you want to know position, one way to look at that is to recognize that if you know a starting place or an initial position, you can just add in the displacement to figure out a new position. This ties right into what we talked about with the fundamental theorem of calculus. So in function notation, using s for position as a function of time, s of t would equal s at a, and a is going to be our initial time, the beginning, plus the integral starting at a and going to any time that you want. So we'll use the same t here, connect those up. And we're going to integrate the rate of change in position, which we know to be velocity. So I'm using a Dumley variable x here. And that's a way you can figure out your positions. For displacement, we've seen this before. Displacement is the definite integral of velocity running from A to B, point A to point B. Those are times. So this is the velocity function. In words, displacement is equal, displacement on an interval, from A to B, we had to add that interval in there, is equal to the integral of the derivative of displacement, which is velocity, integral of velocity with respect to time. Okay, and notice that in our fundamental theorem of calculus, we know that integrating velocity gives us position. So we'll get the position function evaluated at point B and evaluated at point A, and then finding the difference between those. Same thing. But when your question is asking for total distance traveled, we don't care about the direction that velocity puts on things. So in this formula, you'll notice absolute values have been applied to the velocity function in the integrand. That's because we don't care if we're going forward or forward or backward in our velocity. We just care about the speed, essentially. And actually, that's what this is. We take absolute value of velocity, that's speed. So another way to look at this is the total distance traveled on the interval from A to B can be found if you can just integrate the speed function. It's the integral of speed, which I can't spell apparently. Good thing this is blurry and you can't tell. It's the integral of speed with respect to time. Now, if you're going to find the total distance without a calculator, you're going to have trouble with that absolute value. Now, if you have a calculator, this is the way to go. You just go ahead and use your absolute value. But if no calculator is available, you're going to have to handle the absolute value in a special way. So I'm going to move to a new sheet of paper, but right here is a good place to put this information. Okay, so let's consider a velocity function that has both positive and negative values. Maybe it looks like this. Here at time A, B, C, and D, we have the zeros of the velocity function. If I want to know the total distance traveled here, then I'm going to have to set up an integral that integrates the velocity and takes into account the negatives that we want to make those positive. So let me walk you through it. So total distance traveled on the interval, let's go from A, let's go clear out to D. So from A to D, make that a D. If I integrate the velocity function from A to B, that's going to be a negative displacement. Because it's negative, I'm going to change the sign. Because in distance, I don't care about negative, so I need to not care by changing the sign of anything that comes out as negative. The next one, from B to C, notice I'm breaking this interval up and going from B now to C, same velocity function. That's going to be positive naturally, so there's no need to change the sign. So I'm just going to go ahead and add that in. Same thing's going to happen on the interval from C to D that happened here. The integral is going to give me a negative displacement, but I want to counteract that by changing the sign so that it all comes out as positive in my total distance calculation. So I'm actually going to subtract this integral, because by subtracting this already negative value, I'm going to get the whole thing to be positive. And that's going to allow everything to be positive. By taking negatives or subtracting the integrals that are negative naturally, we change their sign and everything counts as positive. Now, That's how you do it without a calculator. If you have a calculator and you have that same velocity function, you can do this calculation a much more straightforward way. For the calculator version of this, the total distance on an integral from A to D, interval from A to D, is to integrate the absolute value of velocity and let the absolute value take care of all those sign changes that are necessary. So going from A to D and just entering this right into the calculator. Now, by putting the absolute value on the velocity function, graphically what that does is it takes that function up there of velocity that had these different intervals where the outputs were positive and negative. Anything that was positive is obviously still positive. But up here, this little valley in the negative region, in absolute value, is going to look like this hill right here. So it's just going to reflect that section above and make it positive. There's already a hill, that's already positive, no change there. But then here's another example. This valley between C and D is going to be an absolute value up here as a hill. The rest of our function looks like this. So we take all the negative regions in absolute value, we get to reflect them across the x-axis. And now when we do this integral running from A to D, everything's already positive and there's no need to do any sign changes because we've taken care of it with the absolute value on the integral, the integrand, the velocity function. That makes it a lot nicer. So you have to do both ways. If you have a calculator, this is definitely the way to go. And if you don't, you'll have to break it down into intervals so you can make the appropriate sign changes. So if you'll flip your page, you'll have an example of just that, and we'll walk through it. So in the example, we're going to suppose the velocity of a particle is moving along the x-axis, and the velocity is given by this function, and time is running from 0 to 2. In part A, we're going to answer the question, when is the velocity moving, or when is the particle moving to the right, to the left, and when is it stopped? Then in part B, we're going to find the particle's displacement for the time interval. In part C, we're going to change the question from displacement to total distance traveled. And here will be a chance where we're going to use the calculator and show how that can be done in one integral. And then finally, we'll do part C's question a second time, this time using no calculator, no absolute value. So we're going to walk through these. All right, so for part A, we need to know when the particle is moving to the right, when it is moving left, and when is it stopped. So the key concept here, again, is that velocity is the function that indicates direction. We've known that, we've used that a lot. Velocity gives us direction of a particle. So we have the velocity function already. There's no need to find it. What we need to do is find its zeros, find its positive regions and negative intervals also. So let me take the velocity function. I'm going to copy it all out, 6t squared minus 18t plus 32. We're going to just set it equal to 0. This is factorable. If I factor this, I'm going to take a 6 out and make that 6t squared minus 3t plus, well, that's not factorable, is it? What am I doing? Oh, I thought that was factorable. I guess I can't take out a 6. Oh, I copied it wrong. Okay, you guys probably caught that too. So this was a 12 all along. Let me fix that here. So I can take a 6 out, and that's going to make it a 2. Let's break down the factors of that quadratic in there. I believe it's going to be t minus 3 and t plus, oh my gosh, try that again. You guys probably have this by now, I hope so. T and 2's and 1's and both negative. T minus 2, t minus 1. Which means that if t is 2 or if t is 1, those are zeros of the velocity function. So let me build a velocity sign chart. I'm going to label it velocity, and it looks like this. Make sure you label it so you don't have the it issue. Time goes only between 0 and 2. I'm not going to make it a number line. I'm just going to make it this interval from 0 to 2. And 1 is also a critical point along with the 2. So we'll put 1 in there. These are t values. Velocity values at time 1 and time 2 are both 0. Then doing a little sign test, let me think about putting 1/2 in as a test for my interval here. 1/2 minus 2 is going to be a negative value from the first factor. And 1/2 minus 1 is also a negative value. So my second factor is negative. 2 negatives make this interval positive. And there's no multiplicity on this, so I'm just going to assume that that's negative. You can verify that if you need to. Okay, which puts me in a position to answer the question. The particle is moving to the right whenever the velocity has a positive sign. And that happens on our interval from 0 to 1. That includes 0. I'm not going to include 1 because that's when our velocity is 0. But before we hit 1, the velocity was all positive, including at 0. I mean, look at that. Look, if you put 0 in, that's going to give you also a positive number. So let's go to left. Moving left would be just the opposite. We're going to move left when the velocity is negative. That happens strictly between 1 and 2, not at the endpoints. And finally, we know that our velocity at 0, when the velocity is 0, that tells us when our particle has stopped. So we have stopped at 2 times, at time equals 1 and at time equals 2. All right, so that takes care of part A. And that work that we just did is probably going to come in handy in just a little bit in other parts, so keep it in mind. Okay, let's go to part B. In part B, they ask for the particle's displacement. Now, displacement is a straightforward integral of velocity. Okay, our time interval was 0 to 2, so displacement on the time interval from 0 to 2 is, by definition, the integral from 0 to 2 of velocity. To make that easier, let's put in the expression for velocity with respect to time. All right, so we're going to just go for our antiderivative. This is going to be t cubed with a new coefficient of a 2. Double check that's 6t squared in the derivative, okay? Then negative 9t squared plus 12t. And all of this is going to be evaluated 0 and 2. Plugging in the 2 first. This is the expression for when time is 2 in there. And we'll take away the position at time 0. Each of these zeros out with a t value of 0, so I'm just going to write that as 0. Okay, now the fun begins. Let's see, this is 8 times 2 is 16. 4 times 9 is 36, and 2 times 12 is 24. And combining all of that together, let me do this part first. That's a negative 20 plus 24. I'm getting a value of 4. 4 units is the displacement on the time interval from 0 to 2. Okay, part C is a very important distinction, not displacement this time, total distance traveled. Total distance traveled. For that, you need to integrate speed. Total distance traveled is the integral of speed. So, total distance traveled on the interval 0 to 2 still is going to be the integral from 0 to 2 of speed. So it's not velocity, even though velocity is involved, it's the absolute value of velocity. So we put an absolute value on this. That's the integral setup. The rest of this I'm going to use my calculator for. So let's look at how that works on the calculator. My preferred method for doing these kinds of problems is to put the function into y1. I'm sorry, this is going to be a little bit blurry. Let me see if I can fix this a little bit. Maybe this will help. I don't know if that's too blurry. Okay, well, listen carefully. I'm going to put into y1 my velocity function. So y1 is equal to 6x squared minus 18x plus 12, excuse me, in my calculator. Then I'm going to go to the home screen. So I'm going to quit out of this, and I'll simply take the integral as I've got it written here. Well, that integral, math 9, goes from 0 to 2. And for the integrand, I need to get the absolute value of my velocity function. So the absolute value function is in your math menu. Go right below your alpha key. Move over, arrow over to the number, and you've got ABS as the first choice. That's your absolute value function. It nicely puts the bars in. Then I can just put in my velocity function, which I have stored in y1. So I'll do alpha trace to access the y1. and finish it off with a dx. Let it do its work. The integral is 6. The integral of speed here is 6. And that means that's the total distance traveled. And I just have to write that down. So doing all that on the calculator, the things you're required to do is write down the integral that you're using, and then you can just give the answer. That's all there is to it. Without a calculator, there's a lot more responsibility that you've got to show some work on. So let's take that next. I can get back into position here. Okay. Okay, so the particle's total distance traveled without using absolute value, that's going to require us to know if the particle ever changed direction. When it was moving forward, we're fine, but if it was moving backward, then we have to make an adjustment to the integral by changing the sign. So the nice thing is back in part A, we did that work. We have a sign chart here to help us. We know the velocity was positive, so the direction was forward or to the right in the time interval from 0 to 1. But in the time interval from 1 to 2, that was a negative velocity. So this is the place where we're going to need to do a sign change on our integral. And we're going to actually split the interval into 2 different integrals. Here's how that works. So the total distance traveled is first the integral from 0 to 1 of velocity. No change necessary. Remember the velocity on that interval. Let me just make a note up here. The velocity on the interval from 0 to 1 was already positive. It's from 1 to 2 that the velocity was negative. So we will add another integral running from 1 to 2 of the velocity function. But that's going to be a negative number. Because of that, we want to change the sign of that to positive. So instead of add, I probably would just subtract that integral. That makes everything positive. All right, now the work of the antiderivative. So I'm going to replace these with the expression again for velocity. And it's 2 different integrals we get to do. Exciting. Okay, so here we go. We already know the antiderivative of this from the previous question. It was 2t cubed minus 9t squared plus 12t, which we'll be evaluating from 1 to 2. And then we're going to subtract. Oh, I messed that up. I messed that up. That should be minus the same antiderivative, 2t cubed minus 9t squared plus 12t. This one evaluated from 1 to 2. Here we go. Plug in your 1. And the first part of this is going to be 2 with a 1 in there. These are just pretty easy. These are just coefficients. Minus, now I'm going to plug in the 0. And that just zeroes out. Okay, so this is the first part. Let me big bracket that. Now we're at this subtraction here. And this is our second interval. Okay, the 2 going in there is going to give me a 16 minus 36 plus 24. And subtract from that, the 1 going in there, similar to over here, that's going to be 2 minus 9 plus 12. And we're all plugged in. And look at this fun arithmetic. Now we get to do a bunch of adding and subtracting. So let's take this group here. This is where I get nervous. You guys might find errors on me. Okay, so we got 14 minus 9. I'm going to call that 5. And then 0. So that's 5. Minus, over here, what have we got? 16 minus, that's negative 20 plus 4. 4 minus, this is 5 still. Okay, so let's lose some parentheses. We're talking about 5 minus, let's see, 4 minus 5 in here is negative 1. So 5 minus negative 1 is 6. And that's exactly the same thing we got from the calculator on part C. Since this is the same question, it should be the same answer, of course. Our method is just a little different. So I'm glad. I think that tells me I did my arithmetic right. So that's all I've got for you. I want you to try your assignment, and we will talk in class about any questions that you might have. Or feel free to text me. We can do a question and answer session on Zoom if we need to. Have a great one, guys.